All right, so you sent over some seriously cool stuff about black holes. I'm ready to dive in head first. We're talking about those cosmic monsters that, suck everything in.
Yeah.
Right. But they're not just science fiction.
Oh, absolutely not.
They're real, and they're out there.
Black holes, yeah, they're definitely one of the most mind-bending things out there. And you know what? Even with all our fancy telescopes and, all these computers and stuff, there's still so much we don't know about them.
Really?
Yeah. But what we do know, well, let me tell you, it's enough to blow your mind.
Okay, speaking of blowing our minds, we've got to start with this guy, Carl Schwarzschild. Imagine this. You're a scientist, right? You're stuck in a trench in World War I,
Mm-hmm.
but you're also, revolutionizing our entire understanding of how the universe works.
Talk about dedication,
Hey,
right?
this guy was serious.
Oh, yeah, he was the real deal. So Schwarzschild, he took Einstein's theory of general relativity, Big Daddy E.
Mm-hmm.
He cracked the code, but in a really, really specific way. He figured out how space-time, and that's the fabric of the universe, right? He figured out how it curves around massive objects.
Okay.
And it's not just some, theoretical curve. Okay, this curve, it's directly related to how massive the object is. The more massive an object is, the more it drags space-time down around it.
Okay.
Kind of, sort of like a bowling ball on a trampoline,
Okay, so that analogy, I get it. But then it gets really wild, right? Because this warping of space-time, it's not just some theoretical idea. It literally changes the way distances work. Remember how the source material was talking about measuring distances near a black hole?
Mm-hmm.
And how it's totally different from, measuring distances in, normal flat space.
Yeah, exactly. So picture this, right? You're drawing circles around a black hole.
Okay.
Now, in normal flat space, the distance between those circles, pretty straightforward, right? Just like the good old rules of geometry, from, what was it, middle school.
Yeah.
But near a black hole, oh man, all bets are off.
What happens?
Those distances, they get all stretched out, distorted. It's like the rules of geometry. They just go right out the window.
Wild. And to actually see this mind-bending concept, the source mentioned something called an embedding diagram.
Ah, yeah, those diagrams. There's something else. They're trying to represent, a three-dimensional reality, but in 2 dimensions on a flat surface. Think of it like pressing a bowling ball, right? A big heavy one into a rubber sheet.
Okay.
What happens to the sheet?
It warps.
Exactly. It warps. That's kind of what those diagrams, those embedding diagrams, they're trying to show us about how space-time warps.
So instead of a nice flat grid, it's more like, I don't know, a cosmic funhouse mirror around these black holes.
That's a good way to put it.
It's a lot to wrap your head around.
Oh, it truly is. It really is. But that's the beauty of it, right? These incredible objects, these black holes, they force us to really, expand our understanding of the universe and how it works at the most fundamental level.
So last time we were really trying to wrap our heads around this whole work space-time thing near a black hole.
It's a doozy, isn't it?
Yeah. But now let's talk about, I don't know, the elephant in the room, or I guess the horizon in the black hole.
I see what you did there.
It's time to face the infamous event horizon. What is this thing?
So picture this. You're free-falling towards a black hole.
Okay.
As you get closer and closer, right, you're approaching this invisible boundary. That's the event horizon. It's the point of no return, where the pull of gravity is so strong that nothing, not even light can escape. Cross that line and, well, you're not coming back.
So this point of no return, this event horizon, it's got a very specific size, right? A source material called it the Schwarzschild radius, I think?
Yeah, Schwarzschild radius.
And get this, they even had a formula for it. R sub S equals 2 GM over C squared. Can you break that down for me?
Yeah, so that formula, as intimidating as it might look, it basically tells us this. The Schwarzschild radius, or the size of the event horizon, it depends on one thing and one thing only.
Okay.
The mass of the black hole.
Really?
Yep, that's it. Not its charge, not how fast it's spinning, just how much mass it's packing. The more massive the black hole, the larger its event horizon.
Okay, so how big are we talking here? Like, if our sun were to suddenly, poof, become a black hole, how big would its Schwarzschild radius be?
That's a great question. If our sun, right, if it just magically decided to collapse into a black hole, its Schwarzschild radius would actually be surprisingly small, only about 3 kilometers.
3 kilometers?
Yeah, about 2 miles. That's smaller than some cities.
Wow, that's both fascinating and slightly terrifying.
Right.
But let's not forget, what really makes the event horizon freaky. the time dilation
Oh, yeah.
and the red shifting. The source material mentioned these.
Right, right. Those are two of the most, well, they're probably the most bizarre consequences of this extreme gravity you encounter near a black hole. So imagine this. Okay. A clock. It's falling right towards the event horizon.
Okay.
As it gets closer and closer to an outside observer, like let's say you or me, that clock, it would appear to tick slower, slower, and slower, and slower.
Are you saying that time itself is slowing down? Seriously?
No, it's wild, right? And it gets even weirder because light itself is affected too.
What?
So as light tries to escape the immense gravity of the black hole, it loses energy.
Okay.
And this causes its wavelength to stretch out, shifting it towards the red end of the spectrum.
We're talking about gravitational redshifting, right?
Exactly. Gravitational redshifting.
So someone falling into a black hole, we wouldn't just see their clock stop.
Mm-hmm.
The light coming from them would get redder and redder until...
Well, until it's redshifted into oblivion.
What do you mean?
It disappears.
Really?
Yeah, it disappears from our view entirely. It's lost, gone, beyond the event horizon.
Whoa. That is both incredibly cool and incredibly creepy.
Yeah.
Okay, so we've skirted around the event horizon, we've felt time slow down, and seen light get stretched into oblivion. What happens if we, what if we dare to look back?
Now that's where things get really, really interesting.
So what happens if we, what if we dare to look back?
Well, you remember how we talked about space-time being, like, warped near a black hole, right?
Yeah.
Well, it's not just time and distances that get messed up. It messes with light itself.
What do you mean?
It bends it, like, in ways that seem utterly impossible in, our everyday lives.
You mean like that crazy picture in the source material? The one that showed, like, light curving around the black hole?
Exactly. It almost looked like an optical illusion, almost.
Right.
But it's not an illusion, though it might as well be. At a very specific distance from the black hole, 1.5 times the Schwarzschild radius, to be precise, light actually gets trapped.
Trapped.
Yeah, it gets trapped in a circular orbit.
Yeah.
We call this region the photon sphere.
So light is, like, literally orbiting the black hole.
Yeah, pretty much.
It's like a cosmic merry-go-round.
Exactly. And here's where it gets really wild, okay?
Right.
According to the source material, if you were, positioned just at the edge of this photon sphere, well, theoretically, you could look out and see, get this, the back of your own head.
Whoa. Seeing the back of your own head, that's a pretty convincing argument for not getting too close to a black hole.
I'd say so.
But, okay, let's say, hypothetically, we were, brave enough, foolish enough to venture even closer. What's waiting for us there?
Well, apart from, certain doom.
Yeah, besides that.
Right, of course. Well, the source material did touch on a rather, how should I put this? Unpleasant phenomenon called spaghettification.
Spaghettification. Okay, that sounds like something you'd hear in, like, a sci-fi movie or something.
Yeah, it does, doesn't it? But it's very real.
Yeah.
And it all comes down to tidal forces.
Tidal forces, okay.
So these are basically differences in gravitational pull that you experience, well, that an object experiences, across its length when it's in a strong gravitational field, like, say, the one around a black hole.
Okay, so walk me through this. What would spaghettification actually, feel like? Asking for a friend, obviously.
Sure, of course. So imagine being pulled feet first towards a black hole. Okay. The gravitational pull on your feet would be so much stronger than the pull on your head.
Oh, no.
And the result, well, you get stretched.
Touched.
Like spaghetti.
Ow.
Hence the catchy name, I guess.
Right. Okay, that is both fascinating and slightly terrifying, to be honest.
It's definitely up there, right?
Yeah, and this is all because of the crazy differences in gravity over such small distances near a black hole.
Exactly. The closer you get to the center, the more extreme those tidal forces become.
Wow. And it's not just about stretching either, right?
Oh, right.
The source material also mentions something about squeezing, I think they called it.
Oh, yeah, the squeezing. Yeah. So imagine being compressed from the sides at the same time that you're being stretched lengthwise.
Yikes.
Yeah, not exactly a pleasant way to go.
Definitely not making it onto my bucket list. But this whole idea that gravity's pull increases as you get closer to something, that kind of sparked a question for me.
The source mentioned that space-time curvature gets more intense as an object shrinks, right? So, theoretically, if we could just compress matter enough, could we create, a tiny black hole?
Ah, now you're asking the big questions. Yeah, that's a question that keeps physicists up at night. But yeah, it's true. In theory, if you could squeeze enough mass, like a lot of mass, into a small enough space, a really small space, then yes, you could, in theory, create a black hole.
So like we could have these like miniature black hole just like zipping around. What would even happen? Would they just suck up everything in their like their larger counterparts? Well, not quite. You see, those tiny black holes, they wouldn't behave exactly like the massive ones that we've been talking about. There's this thing called Hawking radiation, which basically means that black holes, well, they're not entirely black after all.
Whoa, really?
Yeah, they actually radiate energy and they lose mass over time. Eventually, they just kind of evaporate completely.
So they just disappear?
Yep, gone. But here's the thing. The smaller the black hole, the faster it evaporates.
Interesting.
So those mini black holes that you were talking about, they would probably disappear before they could really, gobble up anything too
Oh,
significant.
that's wild. So even black holes eventually just like fade away.
Pretty much.
It's like the universe's ultimate recycling program or something.
Right. The
Amazing.
universe is full of surprises, isn't it?
Yeah, it really is. From warped space, time, and event horizons to, light bending around on itself and the mind-boggling idea of being spaghettified. Today's deep dive into black holes has been, well, it's been a wild ride, that's for sure. So until next time, keep looking up at the stars and maybe, just maybe, steer clear of any black holes that you might encounter out there.